right, aloha kako. Welcome to Hawaii Volcanoes National Park's award-winning After Dark in the Park series. We are pleased tonight to welcome a speaker that I think has done more programs here than any other one individual speaker. That's pretty cool. That's it, drop the mic. This is an incredible treat for me to introduce Dr. Don Swanson. Many of you know Don, he's an absolute legend. If you ever get a chance to meet a living legend, it'll be something like this. It'll be Don Swanson. In 2016, he received the Distinguished Geologic Career Award from the Geologic Society of America. And I love what they wrote about him. If you looked up field volcanologist in the dictionary, you would find a photo of Don Swanson. His approach to our understanding of how volcanoes work is quintessentially scientific, based on systematic observation, measurement, and the formulation and testing of a hypothesis. Throughout his career, Don has steadfastly applied this methodology to address fundamental and often controversial global issues in volcanology. He's definitely not shied away from things that could be controversial. I love when he got interviewed a couple years ago about his work here in Hawaii Volcanoes National Park on Kilauea. He said, "It's nothing that's that overpowering, but when I'm going down to Halemaumau, I'm sometimes thinking, look at where I am," says Swanson, who first set his foot on the Big Island landscape more than 4 decades ago. On a clear day, when you can see the terrain around Kilauea Caldera, I look up and I see Mauna Loa, and I sometimes pinch myself and say, my God, am I really lucky enough to work here? Never lost that childlike sense of wonder. Ladies and gentlemen, Don Swanson.
Well, thank you very much, Dean, for that generous welcome. But I'm going to disappoint you tonight.
Doubt it.
As a field geologist, I'm embarrassed to say that I was not here to see the Kilauea Iki eruption in 1859. So everything that I'm going to tell you is the result of what I learned from talking to people and reading papers, looking at photographs. And then the perspective of 60 years adds something to it as well. On a personal note, I was a senior in college when the eruption took place on the mainland, and I didn't know a thing about it. This was in 1959. I didn't have an interest in volcanoes. There was no internet. There was no television sets in the college dormitories. So this one just passed me by. And it wasn't until I moved to Hawaii about 8 or 9 years later that I really recognized the enormity of this eruption. What I'm going to do tonight is to, first of all, kind of place Kilauea Iki, the crater, in perspective, geographic and historical perspective. Then I'll go through some of the events of the eruption using a number of film clips that Fred Rackel made from the time. And then at the end, I'll be talking a little bit about some of the hazards that these kinds of eruptions create, and talk about some of the things that we don't know, and speculate a bit at the very end when I can duck out quickly to avoid the wrong tornado. Let's see here. For those of you who just have arrived here, Kilauea Iki is on the east side of Kilauea Caldera. It's about 1.5 kilometers by 800 meters in diameter, and it's offset from where the one part of the subterranean magma reservoir is today and was in 1959. Kilauea Iki crater actually consists of 2 craters that are pretty clearly shown in this map from 1912. And we don't know the age of the craters except that they're younger than the caldera, which formed around 1500 AD. Possibly the 2 craters collapsed at about that same time, but we really don't know. We don't know much about its past history. Though we do know that there was an eruption in 1832 and then one in 1868. These were small eruptions, but they changed the floor of the crater. These are before and after photographs taken by Bob Jacobson, a former ranger here. The one on the left shows the view of the 1868 lava flow on the floor of the two craters. You see the trail going down to it. The flows are sparsely vegetated. And then on the right, from about the same vantage point on Byron Ledge, you can see the results of the 1959 eruption. Quite amazing, actually. One thing about Kilauea Iki is that it's the eruption in '59 is that it's famous for its tall fountains, lava fountains, and we don't know of any other eruption from Kilauea Iki that has had anywhere close to such tall fountains. So that eruption is unusual in that regard. Kilauea Iki lies along a trend of eruptive vents that go from Halemaumau to Isla Au Shield and continues into the East Rift Zone. I think this might be a remnant or a rejuvenated part of the East Rift Zone. We know of at least 9 eruptions that have taken place along that zone, starting with the Isla Au eruption in the 15th century. Before Kilauea Iki erupted in 1959, there had been 4 eruptions. We know about the Isla Au eruption, 1832, 68, and 77 nearby. The events immediately preceding the 1959 eruption included an eruption in Halemaumau, forming a lava lake in 1952. This ended the drought since the middle 1930s with no eruption, and it was the first. It's the longest period without an eruption in Halemaumau since 1823. And then in 1954, there was a 3-day eruption that occurred on the floor of the caldera in that zone that connects Halemaumau and Kilauea Iki, as well as in Halemaumau itself. And it followed in 1955 by an eruption in Lower Puna that in many respects resembled that in 2018, though very much smaller than that. I'm not going to be talking about the 1955 or the 1960 eruptions in Lower Puna this evening. I'm going to be talking about what happened at the summit. A tilt meter was installed by Jerry Eaton in late 1956, and I'll get more to that later. But it showed, see, I'm trying to find it showed that there was inflation taking place. That is, the summit was swelling until the summer of '59, and then the tilt flattened off. And then in the month or two just before the eruption began, there was a sharp uptick in the tilt. And so on that basis alone, it was seen that the stage was set for an eruption. But this is the first time, hard to believe, but this was the first time that we really had a good tilt record before an eruption. So there was that uncertainty as well. Okay, now this is by far the most complicated slide I can show you, and I'm going to walk you through it because it really isn't that complicated when I do. This is a map, believe it or not. This is a map. The caldera is right here on this map view. Kilauea Iki is right here. Volcano Village is out in this area here. The golf course in this area here. So this is a map. Everything in blue shows earthquakes that preceded the eruption. And the crosses with dates on them are earthquakes that are unusually deep, 40 to 60 kilometers deep. 40 to 60 kilometers deep. And these earthquakes out here were not well located at the time, but once the seismic network was improved, seismologists now think that they can move these earthquakes into this area here. The orange dots show earthquakes that were taking place immediately before and during the start of the eruption. There are some that are down here right near Kilauea Iki, but the really important ones are up here, and I have this pulsing label to signify that. You see all these orange dots in just within a day or two of the start of the eruption and during the start of the eruption. All of those earthquakes, way away from the summit of Kilauea, were at least 40 kilometers deep. Now, to put this in perspective, most of the earthquakes in the summit region of Kilauea are less than 10 kilometers deep. So to see all of these earthquakes long preceding the eruption and then at the start of the eruption, so deep is unique at Kilauea. So that's what preceded the eruption seismically. The eruption began a little after 8 o'clock in the evening, and it started from 8 fissures that were located well above the floor of Kilauea Iki. The next morning, the word was out. Coconut Wireless was working in those days, and people came to what at that time was called the Byron Ledge Overlook, because you could look across the Byron Ledge. Today it's called the Kilauea Iki Overlook, and people could see the eruption taking place high on the wall, sending lava down into the floor of the crater. And this blow up, I've circled the 8 fissures that opened, 1, 2, 3, 4, 5, 6, 7, 8, high on the wall of the crater. The eruption quickly narrowed down to just this zone here. And this became the main vent for almost all of the eruption itself. But the eruption started as a fissure eruption. Now, I'm going to be showing several plots like this during the course of the evening, and it's very simple. What we've plotted here is the time that fountaining occurred here. Fountaining was taking place during this time here, etc. 17 different periods of fountaining occurred during the 36 days of the eruption. And on the y-axis, we show the fountain height in meters. The highest fountain reached was about 580 meters in episode 15, very near the end of the eruption. And it was very close to that in episode 3. But the record was 580. These fountains, I'm going to be showing some videos of them. They were just wonderful events to observe and interesting ones scientifically. The fountaining occurred in a kind of a pattern. Cyclicity is not a good term, it's kind of a pattern. That there was very low fountaining, as is shown here, and then there was an increase to a maximum height sometime during one of these 17 different episodes. And this would play for some time. And then the fountain would come to an end. It would spurt, and then the fountain would collapse. The spurting and end of the fountain was related to the rise of the lava lake in the crater, such that it really rose up to the level of the vent, and it kind of snuffed out the eruption. This was recognized at the time and is the prevalent interpretation of what happened to it today. So starts small, goes high, ends quickly as the lava lake inundates the vent. And so this plot is like the one that I showed before with the various eruptive episodes. They're all shown in red now, and the black line shows the depth of the lava lake that was fed by the fountain. So you can see that the lava lake reached a depth of about a little over 100 meters after episode 1, and stayed at about that height until episode 4, when it jumped up, and I'll tell you why that is. then the sawtooth thereafter to the end of the eruption, and I'll explain what was going on there in a bit. Fred Rackle, from the mainland, but he was living in Hawaii, in Hilo, took a number of movies of this event that are really quite striking. This is the first one that he took, and it's not very good, but I just want to show you that early, what the eruption looked like earliest, really. I think I was going to, but I'm not. The problem with the system that we have, and I don't know what's going on here. Well, I'm just going to go on to the next slide then and hope that I can get this one going. Oh, the movies aren't going to show tonight, I don't think, folks.
It's okay.
What these two first movies show is that the lava is traveling down into the crater from the vents high on the crater rim, about 120 meters above the crater floor. This video would show that the fountains were not steady. You know, if you turn a garden hose vertically and crank up the discharge, it'll be pretty steady jet coming out of the garden hose. These pulse, and this video was going to show the pulsing nature of these fountains, and every fountain that took place during the eruption had this same pulsing. What that probably indicates is that the gas bubbles that are bursting and driving the fountains, exploding the fountains to great heights, the bubbles are not evenly dispersed in the magma. So that one bubble reaches the surface or reaches a point where it's bursting, followed a short time later, but not immediately later, by another bubble bursting. And so you get boom, 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 pulsing. Oops, that one is not a movie, so I can. Photograph that Jerry Eden took, occasionally there would be sort of a V-shaped fountain, bifurcating fountain with, and this is probably often due to some obstruction that has temporarily fallen back into the vent and is blocking the vertical discharge, and so the lava is squirting out either side, like putting your thumb on a garden hose. And these things usually didn't last very long, but they were quite prominent. And this was at the end of episode 1, this was another pulsing fountain, and it would show that, let's see here. Yeah, I'm just not going to play. This was a pan that Fred Rackle made, showing the lava coming down into the crater and then spreading out and forming the lava lake, or feeding lava into the lava lake. Now we've got it stalled on this slide now. I don't know what the problem is. It's a nice photograph. Enjoy it while you can.
See if it's
no, I'm just using the remote slide.
Now it's spin back.
My hero. How did you do that?
I used the mouse pad here.
Well, that's what, yeah, I was using this, but okay, yeah. Anyway, here you can see that the lava now is spreading outward from the base of the fountain and going down into the lake. This is near the end of episode 1, though not quite there. The lake hasn't risen yet to the elevation of the fountain. Yeah, we can maybe go back if. But how come I can't? There we go. Okay, so this is the first one that. So this is the first image that Fred Reichel took. He was in a plane then, and then he came down to the ground and went to the site. He spent all night out there. The fountains are playing from the fissure. Very small fountains. The episode 1 started very slowly, and the fountains remained quite low for some time. Down in the lower left is the lava lake that's starting to form. You see it's still a long way down. This is still early in episode 1, November 15th or 16th. This is a pulsing fountain, and now you see the pulses that I talked about. People see beauty and power in these fountains, and I certainly do too, but at the very top of the fountain, it seems to me is grace, where the lava is, where the particles have just reached their apex, and I think that's really a beautiful, graceful setting, almost like a lullaby. And then as fragments fall out, it's almost, this isn't quite sacrilegious, I don't think, to say it's a fall from grace, in my view. And here's the bifurcating fountain that I've already showed you that Jerry Eaton photographed. And this is the last day of the episode 1. Again, you can see that the fountains are definitely pulsing. Notice that the spatter is falling onto lava that's already flowing. So there was both ejecta thrown into the air and that fell back, and there was also lava coming directly out of the vent at the same time. And of course, falling ejecta merges with that flowing lava, which here is going into the lava lake.
What are the sparkles about?
Sparkles are, I don't know. I think maybe bubbles that are bursting, and maybe there's a little burning hydrogen or something from them. Sometimes you get sparkles from burning vegetation, but I think this is too far away for that to be the case in this instance. This is looking from the Byron Ledge area. Lava is coming out of the vent. It's feeding toward us into the small west crater lake, flowing beneath the crust and then flowing down a little steep area and spreading out. The main lake is the East Lake, and that's up in the distance, and that's the one that you walk across when you come down the trail from Thurston Lava Tube. By the end of episode 2, there was quite a cone that had been built. That's Pu'upua'i, and it was starting to fall apart. The arrows show lots of glowing or incandescent cracks in the tephra. The tephra is the fountain material that had fallen down, and it was still so hot when it landed that it was incandescent, and so it was quite mobile. And so the cone is beginning to slide downward and outward into the lake. So now this kind of thing where fountains started small, grew big, and then ended abruptly. That continued until episode 4, and then for some reason, even though this was just a small fountain, no higher than 150 meters or so, the lake level rose dramatically. The reason for that, the geologists at the time said, is that the vent had shifted location uphill a little bit. I think what they mean by that is that some sort of a barrier had developed, a dam between the vent itself and the outflow from the vent. And so the lake could rise up until it reached the top of that dam. And so in any case, starting with episode 4, in early December, you can see that the lake level was consistently higher than it had been before. And then after each fountaining episode, you can see that the lake level dropped some, and then when the next fountain occurred, it rose back up to the height of the vent and dropped down again. That dropping is due to draining of the lava back into the vent. The level of lava built up a little bit above the height of the vent, and then when the fountain ended, the lava drained back into the vent. Also, the level of lava can also drop because of outgassing, gas leaving the lake itself. And this is the high lake surface near the end of episode 4. And you can see that the lake is just impinging directly on or against the wall of the crater. There's no evidence there that there's been any drain back, and that's because this is the highest level that lava had reached to this point. So now we continue until episode 8, which was the time at which the lake grew to its maximum depth, of just barely overtopping that of episode 6. Episode 8 was remarkable because of something that it did. The fountain, rather than being vertical or bifurcating just a little bit, just bent right over, and it was angled at 45 degrees toward the north. So there was kind of a fire hose effect, and the fountain arced across the lake, at least part of it did, and landed on the crater rim about 300 meters away. This was a favorite viewpoint. Some of Fred Rackel's videos are taken from that area. And but it was lucky that no one was there during this bombardment that lasted for about 20 minutes. Unfortunately, I couldn't find any photographs of this inclined fountain in the HBO collection. I don't know if any exist or not. But those of you who take the trail along the north rim of Kilauea will walk across this welded spatter deposit. And imagine yourself being there and running like hell when that fountain was directed toward you. So the deepest lake, 126 meters, took place deepened by the end of episode 8. And the next slide then will show what happens when the lake drains away. You see there's kind of a bathtub ring or black ledge or something that is left as lava, which was once at this height, drops down because of draining back into the vent. And at the same time, when the lava dropped down, these islands would be exposed. The islands are part of the unstable Pu'upua'i cone that had slid into the lake at some pre-existing time. They're islands, they weren't floating, they were islands, and you can find on the tops of these things evidence that successive higher stands of lava overtopped them. But then when the lava drained away, the islands became re-exposed. And of course, when you go down there, you can see and climb around on those islands if you want. Now, as the eruption was nearing its end, you can see that the duration of each of these fountaining episodes got very, very brief. Comparing with the early durations that were many hours sometimes in length, these were just an hour, 2 or 3. Although episode 15 had the highest fountain so high that it's hidden by this box about 580 meters high. This is Fred Rackle himself, and unfortunately we don't get a very good view of him, but here he is. Now, see if you don't agree with me that this is really quite graceful, where these spatter clots, pumice just rise, and then the rise velocity dies out, and they fall back down. And now we're going to see some of the high fountains. I'm not sure if this is the highest or not, but it's certainly among the highest. And this is nice because this branch serves as an index, so you can see the spurts nicely as they come up and then pass the branch itself. I'm not sure I believe this. The date on the slide indicates that Don Richter here is observing the vent that had last erupted only 2 days before. Now that's not so bad. You can approach a vent only a few hours after the fountain. I've done that myself. But the point is, how do you get here? You walk across the surface of the lava lake. So I'm not sure. I think there may be an error in the date, but in any case, whenever he visited that, he found that the vent was about 65 meters until it was plugged by greenback debris, choking sulfur fumes, but he heard or saw nothing. So this is the way that the situation looks now and looked at the end of the eruption. The Pu'upua'i is here. I probably should have drawn that a little bit bigger. The main vent was right in here. The West Lake occupying the western crater. The East Lake, which is the main lake, and when you come down from Thurston, you walk across the lake and come up here to the vent. And then south of Pu'upua'i is the main fallout deposit. This is the area called the devastated area, and then the tephra continues far to the southwest from there. I think I joined a lot of park people in disliking that term devastated area because that's something that we imposed. It was something changed. Nature changed the setting, but it didn't devastate the setting. Well, immediately following the end of the 1959 eruption, the activity moved down into Lower Puna, and it's called the 1960 eruption. In fact, the geologists here at the time lumped the two and called it the 1959-1960 eruption. This plot of tilt, remember, it was rising, then it flattened in the summer of 1959, and then it increased. The tilt just plummeted for 6 months during and after the Lower Puna eruption, and then the tilt was up and down, up and down, up and down until the end of 1982. I'll show you a plot of that later. But clearly, the situation was very different following the Kilauea Iki eruption in terms of the summit. Pressure being pressurized than it was before. Okay, now we're back to the earthquakes. This is not quite as complicated a plot. The upper plot shows deep earthquakes. The purples are around 60 kilometers, the blues are 40 kilometers, thereabouts. And this is a plot of earthquakes until the end of 1961. Down here, this is a sort of a time plot from November of 59 here, the time of the Iki eruption, until the end of 1961. And you see this really deep earthquakes. The purple earthquakes occurred in swarms. Now, we haven't seen this since. So this is something that is very puzzling. I've talked to Paula Kugel, one of the seismologists at HVO, a lot about that. We've had a lot of good discussions, and there's no simple explanation for why there were all these deep earthquakes before and for the couple of years after the 1959 eruption. It's really tempting to think that there's a cause-effect relationship there somehow, but we don't really know what it is. Another puzzling thing, it's puzzling only because we don't understand what's going on very well, is that there was no sign of any groundwater being involved in this eruption. Now, because of what happened up here in 2018 and the failure of groundwater to get involved in those little explosions, of course, this is a top priority for us to understand why and how groundwater can interact with rising magma. But it's pretty clear that groundwater did not impact this eruption. Now, conventional wisdom would say that there must have been groundwater present at a depth of a few hundred meters beneath the Kilauea Iki area because there had been no eruption for almost a century. So if some past eruption had boiled the groundwater away, there would be plenty of time for it to come back. Look what's happened in Halemaʻuʻu now, where water has come back within a year after the end of the eruption. But we just don't see any evidence for that water. Conventional wisdom would also say that if water was present, that it should have reacted with rising magma because the magma rose very quickly. The idea is that if there's water, if the rocks are saturated and magma is rising slowly, then the water can boil away before the magma ever reaches it. And so the whole thing is kind of passive and non-explosive. But if magma rises rapidly, there's no time for the water to boil away, and there can be interaction between magma, hot rock, and water that can drive explosions. Well, some very clever mineralogical, petrological study has been made of the Kilauea Iki pumice, and it shows that the rise rate was about 2 meters a second. That's a gentle wind. So the magma was rising from about 4 kilometer depth at 2 meters a second. That's pretty darn fast. And you would have thought that at that velocity, the magma would not have boiled away the water, but instead would have reacted with the water. But we don't see any evidence for that. And so the eruption was dry, not wet. And we didn't give this any second thought until 2018. 2018 has now made us start to rethink all of our assumptions. And now this is a puzzle. And we've got to try to understand it. But right now, we don't understand yet. Yet is hopeful. These high fountains, beautiful and powerful and graceful, do present hazards. And what I want to do now for the next couple of slides is talk only about the hazards created by the high fountains. Now, I think some of you in the audience have heard me talk here about much larger kinds of explosions that we do have evidence for in the past. They were driven at least in part by water. They're very much larger than any of the fountain explosions. I'm not going to be talking about those today. I just want to talk about the fountains such as from Kilauea Iki. I used to think that they would have been very much more common than the water-driven explosions. I'm not so sure now. So in an earlier version of the slide, rather than arguably, I said are probably more common. But I've changed that to arguably now because I really don't know. Anyway, what kind of hazards can we expect from these high fountains? Well, obviously they're going to cause problems locally. This is the area that's the Pu'upua'i overlook now. This is Pu'upua'i itself. There's a lot of spatter on the road, and if you walk out there, you can still see this spatter on the road itself. This is the Crater Rim Drive between the Devastation Trail parking lot and Kilauea Iki. You walk that. Okay. This was plowed out on November 20th. Even during the first episode of the eruption. I guess they were hopeful that was going to be the end, but it wasn't. You can see how already the trees have become denuded of their vegetation by the falling abrasive pumice. And you can see now why the bank along the road that you walk on is so high. It's been plowed up, just like a snowplow plowing the snow out of the road. So Crater Rim Drive through the fallout area was covered. Summer camp picnic area, you wouldn't know where it was except you can find where the outhouse was. And other facilities were damaged. But prudent management in the park kept people from being in this area. And so there was no injury. And future lava fountains are comparable size will certainly have similar effects. Of course, the wind direction is very important in this regard. But what happens if there are fountains that are larger than took place in 1959? Well, we know of 3 examples of such larger lava fountains. And in about 1500, there was an eruption that tossed reticulite all throughout the summit area. You can see how much larger this fallout area is than the area of the 1959 fallout. The reticulite, those of you who live in Volcano, dig it up in your gardens. It's this light, fluffy material that forms a pretty good mulch, actually. That fell out here. And if something like that were to occur, it would impact a far larger area than the 59 fountains. Similarly, in the early 1800s, there were 2 fountains that were much larger than Iki. This one here, and followed soon thereafter by one farther to the west in the caldera, also very much larger than the fallout from Kilauea Iki. And so with these larger fountains, of course, well, it stands to reason that you're going to have potentially a wider area that will be impacted by them, and likely Highway 11 would be impacted, certainly if there's a reticulite eruption like 500 years ago. And as with the lower fountains, the wind direction is all important in this case. So, Iki, the bottom line, Iki-style fountains are probably not going to be too damaging if the trade winds are blowing. The larger eruptions, probably also if the trades are blowing, but if they're really large and last for a while, there could be fallout even north of the caldera.
How high were those fountains?
We don't know, but we can calculate that they were probably around 1,000 meters high, as opposed to the 580 and 59. This photograph was taken on December 13th, 1959. Going and coming. It's also a period piece, isn't it, to see those tail fins on this. Now, I know that there's at least one person in the audience who was here, and maybe you are in this movie, I don't know. Anyway, if you were here, I am green with envy. Because I wasn't. You saw it, I didn't. How unfair can that be? marvelous sight, and it's no wonder that people, I've talked to several people who observed that eruption, and because they could get so close and safely, it's been the eruption at Kilauea. All the subsequent eruptions pale by comparison. So I think almost certainly the next time we have a Kilauea Iki style fountaining event, that the people will be a bigger problem than the hazards of the fountain itself, just managing the people. And you can do it. Where there's a will, there's a way. People so enjoy the tall fountains, seeing them close up in 1959. I think that the same thing could be arranged in the future, but it's going to be more of a challenge because there are many more people here. There was bumper-to-bumper traffic from Hilo to the summit at times during the 59 eruption. Of course, the roads weren't nearly like they are now, but nonetheless, you can imagine with all the higher traffic now what it would be like. Okay, but now I want to just touch on a couple of the scientific legacies. I'm not going to dwell on these in detail, but we learn a lot from these eruptions, and it is important that we learn a lot, because only by learning can we improve our understanding of the eruptions in the future, and so we can better inform the public. So the research is not an egghead kind of thing. It has ultimate payoffs and are being better able to inform the public. And so it's very important that we understand as much as we can about the eruptions, even though this may not make the public, make the news. And we've learned a lot by drilling into the Kilauea Iki lava lake. Many drill holes have been drilled through the lake, even into the floor of the lake. And a lot has been learned about how magma cools and crystallizes in a low pressure environment. And Roz Heltz here has been among the leaders of that study. A terrific amount has been learned from studying the fallout from the tall fountains. And that study has gone on over the years, but recently it's been spearheaded by Bruce Houghton, the professor at Manoa, and graduate students and postdocs of his. So we now know much more about how the bubbles break up the magma, how the clots of tephra flying through the air change shape and change vesicularity, change their bubbles, sizes and numbers with time. All this is very important in understanding the process about how fountains occur. There's been a remarkable amount of information gained on the geochemistry of the lava from the studies that were done in 1960 by the people that were here, Jack Murata and Don Rector, and by later arrivals, Tom Wright and Dick Fisk. These are some of the early papers. There have been many subsequent papers that build on this important world-class chemical studies. And then finally, the chronological narrative of the eruption is unsurpassed in its clarity and detail, and it has the narrative that Don Richter and others wrote has been a standard that we younger volcanologists have really tried to emulate, and I'm not sure we've done a very good job of it. And finally, how volcanoes grow. Jerry Eaton and Jack Murata were on the staff of HBO at the time. They wrote this pace-setting paper that occurred less than a year after the eruption in Science magazine, one of the premier science magazines, journals around. And this set a model that has guided a whole generation of volcanologists. Yes, the model is modified with time, of course, that's the way that science progresses. But that paper stands above the others in terms of providing a comprehensive model for how Kilauea operates. And so finally, I might say that the eruption in 1959 lasted for 23 years. Now, I'd be hard pressed to defend that in a court of law, but I'll show the evidence for that. It's all based on, or it's because of Jerry Eden, who, I don't have heroes in my life, but if I did, Jerry would be my hero. In July of 1956, he designed and fabricated and installed a tiltmeter, wet tiltmeter, electric tiltmeter that immediately began tracking changes at the summit, and the early tilt records that I showed are the result of his work. It's the first true tiltmeter at Kilauea. We still have it today. And what that tiltmeter shows is that there was swelling in the summit before the 59 eruption, collapse during the 1960 eruption, immediate repressurization, inflation, another collapse, on and on until the start of the Pu'upo'o eruption in early 1983, 23 years later. So I can argue that the Iki eruption, and maybe the precursor to that, sort of heralded an important period at Kilauea that's very different from what happened during Pu'upo'o. Now, we don't know why that is. It's a challenging, enduring question that we return to every once in a while. I think maybe there was a less steady magma supply to the volcano during that time, and maybe that's all somehow related to those deep earthquakes that preceded the eruption. It's all nebulous, but there's a lot of food for thought there. In any case, over a beer, I could argue that the 1959 eruption lasted for 23 years. Thank you very much. And I do want to apologize for the audio-visual thing. I want to thank George for coming up with a working laptop, and Dean for figuring out how to run the movies. So I'm open to any questions, but if you don't have any, I can duck out quickly. So. Question?
The gases, I noticed that the temper from that's very foamy, right? So the gases, would they go much further, and how bad would they be in a general setting living in volcano?
The question is whether the gases that are driving the fountains would present a problem downwind. I guess that's what. Yeah. And the answer is yeah, but it's pretty brief because the fountains are pretty brief. So, for example, the Pu'upo'o fountains and the Mauna Ulu fountains before that were nearly as high as the Kilauea Iki fountains, but didn't create any long-lasting hazard under themselves. But it's for those two eruptions, it was the activity between the fountains that created the main gas problem. We didn't have that at Kilauea Iki.
My impression was that the trade winds were blowing when this happening was happening.
Yeah, the question is were the trade winds blowing when this was happening, and the answer is yes. And you can tell that, well, people knew at the time, but you can tell that from the distribution of the fallout was toward the southwest, and the trade winds were blowing it going in that direction.
All the people watching the trades were coming from behind them.
Yeah, they were off to the side, really. They were to the east of there, except for those that were north, and had good visibility, except for that one time when the fountain bent over and tossed up in their direction. Yeah.
Were there any xenoliths inclusions of rock from a deep mantle evident in the Kilauea Iki?
The question is, were there any fragments of the mantle, the deep rock in the earth, erupted during the Iki period? And the answer is no. The pholitic, the kind of basalt that's erupted from Kilauea doesn't carry many, if any, deep inclusions in it. But one thing that has been discovered is that there are some mineral olivine xenocrysts that form. There are crystals that were foreign to the magma that have been found in the magma, not only at Kilauea Iki, but also down in Lower Puna. And I don't think these are coming from the mantle, but they're coming from some deeper storage process or area along the way.
Is that the olivine on the west bay?
Bobby, the question is that the olivine on the west, in the west bay, the west lake? That is probably pretty typical, actually. Of the entire eruption was loaded with olivine, much more so than most summit eruptions, and that's I should have emphasized that that's another difference that Kilauea Iki presented as compared to the other early summit eruptions. But that's kind of typical, actually. Sometimes in the lake margins, in the drainback levees and so forth, liquid will drain away, leaving some olivine crystals, and so there's sort of an artificial enhancement or enrichment of olivine, but it's not great. Yeah.
Since we have you here tonight, would you be willing to comment, and since we know you spend a lot of time in the field still, would you comment on the current lake in Halemaumau and also those growing sulfur deposits all along the sides of Halemaumau? What your own observations are at this time?
Did everybody hear the questions? Yeah. I think that the sulfur deposits are coming from along a ring fracture that is kind of defining the main subsidence area in Halemaumau, and that is the fracture is providing passageways for hot sulfur-rich gas to rise. The lake, or pond as I prefer to call it, because it's so tiny. I know we have Lake Waiau, but it's pond is a better term. Anyway, that is destined to fill. I think up to a level that would be another 60, 65 meters higher than lake level is today, if the level is going to be even with the level of the water table that we find in a drill hole a kilometer farther south. That's a big question because there are dikes that in the past that have intruded into the summit area, and they can impound water. There are lava tubes that can serve as transport mechanisms or pathways for water. And so the reality is probably far different than the simple model, but the simple model would suggest that the lake would rise another 60 or 65 meters above where it is now. Now, to my mind, the presence of the lake brings to the forefront the possibility of later magma-water interactions. It's not necessarily the lake per se, but the lake is a visible evidence of groundwater coming into the system. What happened before 2018, I think, is that the feeder, the conduit feeding the lava lake in Halemaumau had boiled away the groundwater. And so the conduit was dry, and as a consequence, we didn't have water-driven explosions in 2018. But now water is starting to come back in, the system is cooling down, And the lake is a manifestation of that, but even if we didn't see the pond, water would be present. If magma rises slowly through that system, then conventional wisdom, which is probably wrong, would say that the water would be boiled away a second time and we wouldn't get explosion. But if magma rises rapidly, who knows? And so it's a big learning experience for us. And I've told many people that this period of time that we're in now, since the summit collapse of 2018, is the most exciting time that I've been at Kilauea. We're not seeing any surface expression. We're not seeing the glorious lava flows and the fountains, but it makes you think. And that, to me, is really what's exciting about studying the volcano. Yeah, question back there?
Can you explain the difference you see on the surface of the east and west lakes in Kilauea? They're very different.
Yeah, the East Lake, the main lake, the one that's been drilled, has had crustal overturning. So the crust was renewed frequently because bubbles would float up and be trapped by the crust. There's a density inversion. The crust would be less dense than the bubble-rich magma lava. The bubble-rich lava would burst through and resurface the lake, not flowing very far laterally. So you don't have Pahoehoe toes and rubble and so forth. The West Lake did not have that regular kind of filling. It had a lot of surface flows coming across it, and it really isn't a lava lake in the sense that the East Lake is, in that it's a much more complicated sandwich, I think, of surface flows and little ponds and so forth. So it's quite different.
All right, we're going to go ahead and actually end it right there. But if you didn't get your questions answered, please come up afterwards. Don will still be here. So thank you guys so much for coming out tonight. We should be right on 20. So thank you so much. That'll give permission for people to go that have to go. I was going to book another program in November for After Dark in the Park, but everybody said, I got to follow Don Swanson? No! So instead, we've got 3 coming up in December. The next one, December 3rd, for those of you who've been following the reintroduction of Allah to the wild, we have the 2-year update. They're coming in to talk about it. So that'll be a lot of fun. If you didn't get your questions answered, please come on up. Talk to Dr. Swanson. Thank you so much.